The purpose of this lesson is to teach you how to solve a first-order linear differential equation that might have an inhomogeneity in it. And if you use what you know about classification vocabulary for differential equations, that means we're talking about an equation of this form: y prime plus a of xy equals b of x. Right? This is what makes it first order, that there is just a single derivative. Linearity we haven't talked too much about yet, but it just refers to the fact that the dependent variable is never multiplied by itself or any derivatives of itself or appearing inside of some nonlinear function. It only appears in a linear manner. And the inhomogeneity, of course, is this term over here. Note that if there's no inhomogeneity, meaning if b of x is 0, then the equation would be y prime plus a of xy equals 0, which is separable. So you could also, in that case, solve it by separation of variables. But I'm going to show you how to do this using an example, but I'm going to tell you the overall strategy. The overall strategy is to multiply the equation through by something so that you can write the terms on the left-hand side as the derivative of a product. I'll say that again. You want to multiply through by something that lets you write the left-hand side as the derivative of a product. So we'll take y prime plus xy equals x with y of 0 equals 10. And the thing that we have to multiply through by is e to the antiderivative of the coefficient of the y term. That's the a of x term, right? So for us, the a of x is like x. So I'm going to figure out what's e to the antiderivative of x. Well, that's e to the 1/2 x squared. And I'm now going to multiply through the entire equation by that factor. So I get this. I get e to the 1/2 x squared y prime plus 1/2 e to the 1/2 x squared xy equals e to the 1/2 x squared x. Why did we do that? What was so special about that factor? Well, you now recognize something, right? You recognize that this whole thing is just the derivative of a product. It's a product rule, right? And the thing it's a product of is the derivative of y times e to the 1/2 x squared, right? So when you do the product rule, if you leave this part alone, differentiating this part, you get the first term up here, e to the 1/2 x squared y prime, and then if you differentiate the first part of the product, leaving the second part alone, you get e to the 1/2 x squared times x from the chain rule times a y. All right? And then on the right-hand side, we still have our e to the 1/2 x squared times x. Why did we do this? Well, this equation, you can now just anti-differentiate each side. On the left-hand side, it kills the d dx, so you get e to the 1/2 x squared y. On the right-hand side, we can anti-differentiate this term. We get e to the 1/2 x squared plus a constant. Then we just have to isolate y. So I'm going to divide through by e to the 1/2 x squared, and I get y equals 1 plus c e to the minus 1/2 x squared. You can go ahead and plug in the initial condition, y of 0 equals 10. That tells you 1 plus c e to the 0 must equal 10, so c is 9, and therefore y equals 1 plus 9 e to the minus 1/2 x squared. All right, let's do another example. So we're going to look at 1 plus x y prime plus y equals 1 plus x cosine x with y of 0 equals 2. And the first thing I'm going to do is try to put it in this more standard form where y prime has a coefficient of 1. So I divide through to write this equation, y prime plus 1 over 1 plus xy equals cosine x. So my integrating factor is going to be e to the antiderivative of this term. So that's e to the antiderivative of 1 over 1 plus x. That's e to the natural log 1 plus x. But the exponential function and the natural log are inverse functions, so this just gives me 1 plus x. So now I'm going to multiply through by 1 plus x to get 1 plus xy prime plus y equals 1 plus x cosine x. Oh snap, that's the original equation that I started with. So actually in its original form, it was better than in standard form, but you might not recognize that. So it's always a good idea to start off with standard form if you can apply this method, and then go ahead and find your integrating factor. Alright, so let's go ahead now and recognize that the left-hand side here is the derivative of a product. It's d dx of 1 plus x y, and on the right-hand side we have 1 plus x cosine x. So now we're going to go ahead and anti-differentiate each side. On the left, we get 1 plus xy, because we kill the d dx. And on the right, we have whatever is the antiderivative of 1 plus x cosine x. Well, it turns out you can evaluate that integral by integration by parts, and if you push that through, you get cosine x plus sine x plus x sine x plus c. So to isolate y, I'll divide through by 1 plus x, and I get this final answer here, cosine x plus sine x sine x plus c over 1 plus x. If we plug in the initial condition y of 0 equals 2, we find out that 1 plus 0 plus 0 plus c all over 1 has to equal 2, and therefore c equals 1. And our final answer is this expression here. Okay, so again, integrating factor. Now, at this point, you've seen two examples, and you might be asking, why is that the integrating factor? And the best way to see this is just to go back to the original equation here, right? So, and derive the answer yourself. Meaning, for this equation, the integrating factor would be e to the antiderivative of a of x dx. I urge you to actually do this. Multiply through the equation, multiply it through by that factor, apply the product rule in reverse, anti-differentiate each side, and you'll get the answer, right? So every step that we applied to these specific examples of solving differential equations with an integrating factor, you can apply to this general problem up here, and that's how you see that this method works. All right, thanks for listening.